Welcome to the Crazy Hat Chemist. So another video here on Kinetics. So let's get moving. Bam! So today we're talking about the integrated first order rate law. Okay, we're going to integrate the first order rate law. Okay, and then what are we going to get? A really important equation that we're going to be using for kinetics and oh so much more. Okay, this integrated rate law actually works for a first order process of any kind that's dealing with kinetics. And it always works with radioactive problems because all radioactivity undergoes a first order kinetics rate law. So you have to use this equation for any kind of radioactive problem. Okay, so here is the first order integrated rate law right there. Okay, so I'm going to delineate which each of these parts here mean for you, and so then that way you know where to plug in values and how to use it and how to rearrange this. Okay, T is for time, and time can be in minutes, seconds, days, years, doesn't really matter what it can be in. Any of those would be perfectly fine. K is the rate constant. Just like in the rate law, K is the rate constant. The K is still the same rate constant. Now the rate constant here is per unit time. So you're going to make sure that when you are plugging in values into this equation, that your time, that is T time, is going to be the same as the rate constants per unit of time. So if the time is in seconds, then the rate constant will be per second. If the time is in minutes, then the rate constant will be per minute. Okay, notice that there's a negative sign there in the front. That deals with that right-hand side of the equation very nicely. Then the next thing here is the natural logarithm, and that is ln. Now, I'm hoping that you remember way back from your Algebra 2 classes, or maybe even in pre-calculus nowadays, okay, and how to work with natural logarithms. Okay, and so this one right here is a division. And so I want you to think about what you do with the division problem here. So we got natural log of, that's ln of x sub t divided by x sub 0 or x sub naught. So how do I separate that out and not make it a division problem? I'm going to make it a subtraction problem. So natural log of x sub t minus natural logarithm of x sub 0 or x sub naught. So hopefully you remember that. Okay, if not, then review that. It's not very difficult. Okay, the amount of time, so the amount at time t, okay, so this brackets generally means a concentration. So x is the amount of whatever it is, okay, at time t, and that corresponds to the same time t on the right-hand side of the equation. And then this is the amount at time 0, and that's otherwise known as the initial concentration. Okay, if you have percentages, then the initial percentage is of course going to be 100% because you're always going to start off with 100%. Okay, hopefully that makes sense. Okay, now if you the other part of this is the change in the fraction remaining is after a certain amount of time has elapsed is x sub t divided by x sub naught. Okay, that's the fraction remaining at that, again, same t time. Okay, some of you have incorporated into or moved on into a calculus-based mathematical course. And if you have moved on to that calculus-based mathematical course, these two equations right here work very nicely for integrated first order rate law, and some calculus-based math books incorporate this equation instead of the one that I have in yellow. But I will be using for this course the one in yellow because all textbooks in chemistry use the one in yellow. So that's the one that we'll be using here. Remember the integrated first order rate law. It's very important. Natural log of x sub t divided by natural log of x sub 0 is equal to negative kt. All right. I am the Crazy Hat Chemist, and oh, I got a little bit of humor here for you. Okay, so what is the favorite baseball player of the elements in group 2A? So you got to figure out where group 2A, and that starts off with beryllium and goes down to radium. So what do you think that is? By the way, what group is 2A? You got the alkaline metals and then the alkaline earth metals. So, of course, that favorite baseball player would be alkaline. And if you don't know who alkaline is, then ask your parents and they might know, or maybe even your grandparents. Okay, so alkaline earth metals, that is group 2, and that's why it's group 2 favorite baseball player. And of course, alkaline, he was a really down to earth because it's the alkaline earth metals. And there's actually a picture of alkaline. He played for the Detroit Tigers. Okay, I am the Crazy Hat Chemist, and I got a crazy hat here for you. And this is called a cork hat. And it's it's in Australia, from Australia. It's to keep away pesky little flies, bugs, or whatnot, and maybe even, I don't know, pesky little students. I don't know. So give me a thumbs up if you like that video. Subscribe to my YouTube channel, and I'm going to see you next time for more kinetics problems. Bye for now.